Hello students, in our first video on mechanics of solid, we have discussed about simple stress and strain and also the types of stresses. Now in this video, we are going to discuss the limit of elasticity of the material, Hooke's law, elasticity modulus, rigidity modulus, bulk modulus, and also the relationship between stress and strain. Let us now see the next video sincerely, and if you have any doubt, you can ask me in comments. So let us see now. Elastic limit. There is a limit of elasticity of every material. In other words, every material behaves elastically up to certain limit of loading, beyond which, if it is loaded, the material undergoes plastic deformation. Therefore, we use materials with working load within its elastic limit. The elastic limit of different material is different. The elastic limit of steel is very high compared to rubber. That is why steel is said to be more elastic than rubber. So the summary is every material has its elastic limit. Up to some limit only the material behaves like elastic, beyond which it becomes plastic. And we have to use the material within its elastic limit. We have to apply load on a material within only its elastic limit. Okay? Now, to solve many mechanics of solid problems on simple stress and strain, a very important law is there, that is Hooke's law. So what is Hooke's law? Hooke's law, it states that when a material is loaded within its elastic limit, the stress is proportional to the strain. So it is the scientist Robert Hooke who developed this law. After a number of experiments, he concluded that the stress is always proportional to strain if the load is within its elastic limit. So he concluded mathematically that stress is proportional to strain. And this is Hooke's law. Now, modulus of elasticity. Modulus of elasticity symbolized as E. It is the ratio between direct stress and direct strain, both tensile and compressive, within elastic limit. Mathematically, it is capital E is equal to stress by strain, sigma by E. So modulus of elasticity is nothing but it is the constant of proportionality that has been given by Hooke's law. Hooke's law only proved that the stress is proportional to strain, and Young's modulus, that scientist Young determined the value of the constant of proportionality, which was known as Young's modulus. The other name is modulus of elasticity. This is also called elastic modulus. So it is capital E, sigma E by E. So the next is modulus of rigidity, C as a symbol. It is the ratio between shear stress and shear strain within elastic limit. Symbolically, it is C is equal to shear stress tau by shear strain phi. The third one is bulk modulus, K. It is the ratio between normal stress and volumetric strain within elastic limit, of course. K is equal to sigma by EV. Sigma is the normal stress, EV is the volumetric strain, that is change in volume by original volume. This is also one modulus. So three types of modulus we have discussed. Young's modulus or modulus of elasticity. The number two was modulus of rigidity, and the third one is bulk modulus. These three moduli help in solving many mechanics of solid problems on simple stress and strain. And now the simple stress and simple strains are actually related in such a manner that it can be shown by a curve. The relationship between stress and strain for a mild steel has been shown here. We will discuss how they are interrelated to each other. Figure shows stress-strain curve of a mild steel specimen when subjected to tensile load. Strain is drawn along the x-axis and stress is drawn along the y-axis. Then this curve depicts or describes the relation between stress and strain in the duration of the test on the specimen. If the plot between OA, look at here, OA, is a completely straight line, perfectly straight line. So the plot between OA is a straight line indicating that the stress is proportional to the strain. The stress corresponding to point A is called the limit of proportionality. At this point, the stress is here, this stress is limit of proportionality because up to point A, the specimen remains purely elastic. Beyond this point, the stress is no more proportional to strain, even though the material remains elastic up to point B. The material remains elastic up to point B. The stress at point B is called the limit of elasticity. If the specimen is stressed beyond elastic limit, plastic deformation takes place. In the range B to C, the strain increases with almost constant stress. At C, the stress at C is called upper yield point. So you can look at here, between B to C, there is no rise in stress. The B and C is, the height of B and C are almost same. There is no change in stress, but the abscissa x coordinate is more of C than B. That means strain has increased, but stress has not increased. That's what it is told here, that in the range between B to C, the strain increases with almost constant stress. The stress at C is called upper yield point. Beyond the point C up to D, the deformation continues even with reduced stress. At point D, which is called lower yield point, the molecules inside the material reorganize to resist further deformation. So you can see here at point D, which is called lower yield point, here the molecules inside the material reorganize to oppose the deformation. So stress is further required if you want strain. So stress is increasing for further strain. With increase in stress and strain, the material reaches a point E where the material develops necking. You can see here from D, if further stress is increased, with the stress and strain increasing, the material reaches a point E. At this point, the material develops necking. That means thinning. The diameter reduces abruptly. The stress corresponding to this point E is known as ultimate stress. Because of necking, The strain continues with decreased stress and breaks at F. Now look at here. This point E, the stress corresponding to this point, this stress, this is ultimate stress. That means highest or maximum stress that the specimen can take, beyond which they starts breaking and splitting or thinning. Finally, it fails at F, breaks at F. So we can say the maximum stress that the material can take is the ultimate stress, which is indicated by this point E. Okay, that's all.